Hey guys, good afternoon. The first problem in this chapter deals with the concept of center of gravity. In this one, we're given a picture of a box and a plank that are positioned on top of a fulcrum. The plank is 2 meters long and has a mass of 25 kilograms, whereas the box is 75 centimeters wide and has a negligible mass. Our plan is to fill this box up with sand. And the reason we're doing that is because this plank has a very special quality. It's one with a non-uniform mass distribution, which causes its center of gravity to be shifted toward the end on the right, as indicated by the crosshair symbol in the picture. Recall that an object can only be in rotational equilibrium if its center of gravity is found within or directly at its points of support. So our job is to figure out how much sand needs to be added to the box so that the center of gravity of the system will meet those requirements. The way that we'll do this is by using the center of gravity equation, which looks like this. Starting from the left-hand side, we have xcg, which represents the x position of the center of gravity of the system. On the right-hand side, we follow the same type of labeling convention where x sub s represents the x position of the center of gravity of the sand, and x sub p represents the x position of the center of gravity for the plank. Last but not least is the w variable, representing the weight of each object, with w sub s for the weight of the sand and w sub p for the weight of the plank. Now, before we can start using this equation, we have to deal with the fact that it contains too many unknowns. The weight of the sand is an unknown because it contains the unknown mass of the sand. Additionally, all of these x positions for these centers of gravity don't have any numerical values assigned to them. So what we'll need to do is follow a quick 3-step process before we can come back to this equation and algebraically solve for what we need. In the first step, we're going to locate the center of gravity for the box of sand. Once we find it, we can move on to step 2 and start setting up our horizontal coordinate axis. This will allow us to place numerical values on all of those center of gravity positions. And then once all that's done, we can return to the center of gravity equation and then use it to finish the problem. So let's get started with step number 1. Here we have our box, and we're going to imagine that it is completely and uniformly filled with the sand. Now there's a couple ways that we can locate this center of gravity position. We could go the difficult way and use calculus, which would take us a little while, or we could go the much easier way and take advantage of the geometry of the shape of our box. The easier way goes something like this. The center of gravity for an object will always be found at its geometrical center, or centroid, if it has a uniform density and the acceleration due to gravity has the same value everywhere along all points on that body. And since our object satisfies both of those requirements, there's no need to do the calculus. We can skip right past it. We already know that the location of the center of gravity will be found right in the very middle of the box, at a horizontal extent of 37.5 centimeters from the left end. We don't have enough information about the height of the box to find the vertical extent of the center of gravity position, but thankfully, we don't care. It's not useful to us in this situation. We're only interested in the x position of where that might be. So with that said, step 1 is complete, and we can move on to step number 2. Here in this part, we're going to be setting up our horizontal coordinate axis, but we need to be really careful about how we do it. If we place x is equal to 0 in a bad position, we'll end up with a wrong answer. Here's a really helpful tip to know where it should go. Whenever you're calculating the position of the center of gravity or center of mass for your object, do not place the origin of your coordinate axis or coordinate system in the same position as a force. In our situation, the first force that we encounter before we add sand to the box is the weight of the plank, which acts from the point x sub p. Then once the sand is added, we have two other weight forces acting at x sub s as well as x cg. So these 3 points are off limits when it comes to the origin of our coordinate axis. But outside of these 3 points, everywhere else is fair game for x is equal to 0, as long as you are consistent with your choice. What I would recommend personally is placing x is equal to 0 over at the end on the left side of the plank, because if you do this, all of the x positions for the centers of gravity will have positive values, and it tends to be easier to deal with positive numbers as compared to a bunch of negative ones. So now we have the weight of the plank and numeric values to assign for the positions of all of these centers of gravity. This means we can finally move on to step 3 and return to the center of gravity equation. The first thing we should do at this point is switch out the weight of each object with its definition, mg. Notice that both terms in the numerator as well as the denominator contain g. This means we can factor it out and cancel it. Once we do that, take a close look at the result that we're getting here. This says that the x position of the center of gravity of our system is equal to the exact same expression for the x position of the center of mass. This result is not a coincidence. Rather, it's a consequence of all points of our system experiencing the same value of acceleration. So it might be helpful to remember that if g is the same everywhere for your system, the center of gravity will be found in the exact same spot as the center of mass. But anyway, let's move on. What I'll do next is multiply both sides by the sum that's found in the denominator on the right-hand side. With that complete, we can distribute the x position of the center of gravity of the system into the parentheses on the left. Notice that we have terms containing the mass of the sand and terms containing the mass of the plank. What we should do is take all of the terms that contain the mass of the sand and place them on one side, and take all of the terms that contain the mass of the plank and put them on the other, like this. That kind of a setup allows us to factor out the mass of the sand, and then divide both sides by the difference found in the parentheses over on that left side. Now we have an expression for the mass of the sand, just like we wanted. Once we plug in our numbers and then simplify, we end up with the following ratio being multiplied by 25 kilograms. We find that our system will only achieve rotational equilibrium if we add a mass of sand equal to 20 kilograms to the box. And that's it. We're all done. Thanks for watching, everyone. Have a great day.